Hey folks, welcome to the first lecture for this last part of the course. Our goal here is to explore some of the mathematics of infectious disease models, and that's kind of relevant right now. And so we'll see some of the underlying mathematics behind what we're hearing on the news. They talk a lot about modeling, and we'll see where some of that modeling at least begins. We're obviously not going to get into the depth of modeling that's actually driving public health decisions right now, but we'll see the basic format of the sort of mathematics that's being used. I want to say up front, I'm not an expert on mathematical disease models. I'm not a mathematical epidemiologist. These are people with, deep expertise. And so the experimentation that we do with these models, I don't want you to be treating it as predictive of what's going on in the world around us. My goal here is to give you some insight into the discussion that's being had amongst experts. We're obviously not going to be able to reproduce their results or argue with their results, but hopefully we'll be able to understand what they're saying and where their ideas are coming from at a deeper level than you would without, playing with these models. So earlier in the course, we looked at the discrete SIR model, if you remember, and so we've already got some expertise, or experience, I should say, with this kind of modeling. And so we're going to build on what we already know in the discrete case, and all of these are going to be systems of differential equations. So they very much build on what we've talked about earlier in the course. The last chapter was about systems, and we're going to build on that information and that experience and expertise that we've built up. And we're going to look primarily at two different focuses for disease modeling, the so-called epidemic models and then the endemic models. Epidemic models are what we are facing now, where a disease breaks out over a short term and spreads, right? So you don't get long-term factors entering into it because it's a very short-term event. Hopefully this is a short-term event. So an epidemic model might describe the outbreak of the coronavirus we've got now, or the outbreak of a flu in a particular season, whereas endemic disease modeling is about diseases that become endemic in a population in the sense that they come back every year, maybe like the flu, or they are not seasonal at all, something like the HIV infection. Modeling is going to be an endemic disease model because HIV exists in the community. And so the modeling involves seeing how that evolves over long periods of time. The key differentiating factor between these two types of models is really whether there are new populations coming in, whether the disease lasts long enough for people to be dying during the course of the disease, dying of natural causes, babies being born, maybe people dying of old age, whether there's fresh turnover, if you like, in the population. If that's the case, then you're usually talking about an endemic model, right? The population is doing what the population does and the disease is there over a long period of time. Whereas an epidemic occurs over a short period of time where you could, it's a reasonable assumption to say the population is essentially fixed during that time because people aren't dying of other causes, people aren't being born. We can kind of ignore those factors. And as we've talked about throughout this modeling course, simplifications are key. And so that is the kind of simplification we'll be making. We have a fixed population during this epidemic. So the models we will be talking about really began with a series of papers from the 1920s and 30s by Kermick and McKendrick, and these led to the SRI model that we've already sort of seen a little bit. And our first goal is to really derive those SIR models again from first principles with reasonable assumptions and thinking carefully about the assumptions that we're making. And these assumptions are really about splitting the population into subgroups. That's the key idea of these models. We're going to split the population into subgroups, and we've already seen those subgroups, right? We talked about susceptible individuals. These are the people who can be infected. There's infectious people who currently are infected and have the disease. And then we talked about the removed and recovered group of people. They're the people who are no longer infectious, or they might have died, but either way, they're no longer available to be infected, and they're not currently infected. So in a sense, they've been removed from the action, if you like. And that's where the term SIR is coming from, because this is the susceptible, the infected, and the recovered groups. These aren't the only groups you could have, and we're going to talk about these extra models a bit as we have time, but you might have exposed people. There are diseases where you can actually have the disease for a while before you become infectious. So it's like a halfway house where you're hanging out with the disease. You may or may not know it, but you're not yet able to pass that disease on. And then there's the idea of maternal immunity, where the mother might be able to pass on enough antibodies to make the baby immune. perhaps for a while, perhaps permanently, perhaps not every child gets the immunity. So these are extra groups we can add on. If you think about the coronavirus, it seems, from what I understand, to be immediately infectious, but not immediately symptomatic, which is almost the opposite of this exposed group. This exposed group are people who have the disease but aren't yet infectious. They probably know they have the disease, but they're not yet able to pass it on. Whereas COVID-19, the disease caused by the coronavirus, actually has a period where you're infectious, but you may not know that you have the disease. And so perhaps we would want to create a new subgroup to model the coronavirus, in which you're not yet counted as an infectious person because nobody knows, and yet you're still able to pass that disease on for a period of time. So these are the kind of things we can play with. These are the ideas we're going to introduce over the next week, are going to let us explore what's happening right now with the coronavirus with our simple models. So let's get going and rederive from scratch this basic SIR model that Kermick and McKendrick built almost 100 years ago. So this basic SIR model builds on the ideas we've been talking about. The population size is assumed to be constant. Remember, we want to make simplifications because simplifications help us do our job, right? Simplifications help us make progress. They might not be reasonable, but they help us get going on the modeling process, and then we can refine it as we go. So we're going to assume that the total population size is constant. So we might be talking about a city, we might be talking about a country, but the population remains constant during the epidemic that we're interested in. And then we're going to divide, and this is the key SIR assumption, we're going to divide the population into three groups. That total population N is going to be split into people who are susceptible, for people who are infected, and people who are recovered. And we're going to label them S, I, and R. So this picture here is meant to represent the total population. So inside this triangle we have N people, and they fall into one of those three categories. And those three categories will change over time. So these variables are time dependent, because people are going to be susceptible but then get sick and become infected, and then some of those are going to get well, and so they're going to be recovered. And so there's going to be a flow between those groups. And that flow is going to take susceptible people, people who are well, and turn them into infected people. Some of those people are going to get infected. And then over time, some of those infected people are going to recover. And that's the essential dynamic in the model, because we're going to assume that recovered individuals can't be reinfected, which means once you're removed, or maybe that means dead, but either way you're removed or recovered from the disease, we're going to assume you're not reinfected. Now, scientifically, I think that's an uncertain prospect right now, because the coronavirus, it's not known whether people can be reinfected or not. But our model, the simple SIR model, takes susceptible people. Some of them will get infected, they will recover or perhaps die, but either way they end up in this final grouping, this R. And our job is to study how people who are susceptible may get infected and then become recovered. So look at the time dependence of those variables. Look at the dynamics between those variables that are represented by this model. Something that's worth noting as well is that we're going to assume that infected individuals are also infectious. And as I mentioned, that's that's definitely true for the coronavirus as far as I'm aware. But it's also possible that there's in-between step here where people don't know they're infected yet, but they are actually infectious. So we're just going to assume as a simple beginning that at the moment you have the disease, you're immediately infectious. So in a sense, in our minds, we can think this infectious group includes all the people who have the disease and can pass it on at any given time. Not all of them actually might know that they have the disease. And that's what's particularly nasty about the coronavirus or the COVID-19, is that you can be infected and not know it and still pass it on to other people. So these are the basic assumptions we're going to use. And so mathematically, our job is to describe those three functions, S, I, and R, as functions of time. So I'm going to treat them as continuous functions of time. And obviously they're changing, which tells us that the mathematical structure we're going to be dealing with here is differential equations. So it's these rates of change that are going to lead to the differential equations, a system of them, one for each of the variables, dependent variables S, I, and R, and T is going to be our independent variable. Let's sit down and carefully derive the equations from the basic kind of structure of disease spread. Okay, so three key quantities we need to know to be able to quantify how a disease is spreading in a population are given here. The first one is the duration of infection, and that's pretty straightforward. If you get the disease, what's the average length of time that you would expect to be sick? So for COVID-19, that seems to be about 14 days, right? It seems to be about 2 weeks is what people are estimating. The probability of transmission, the transmissibility, if you like, that's what I'm calling TOR here, that is the probability that you're going to get the disease if you interact with an infected person. So just because you see someone who's sick doesn't mean you're going to get the disease. Even if you interact for an extended period, there's only some certain probability that you will get the disease, right? And so this is like the average probability that you will get the disease if you have a meaningful interaction. So the way they talk about COVID-19, that's like a 30-minute interaction, then you've got a good chance of having got the disease. Maybe it's a 30% chance. I don't know. I'm making that up. But this is just the probability that you'll get the disease through interaction with an infected person who's infectious. And the last one is the number of contacts per infected person. And that turns out, according to epidemiologists, to be roughly constant in a given culture. So a given culture will have a roughly constant value across the population. So we're assuming sort of well-mixed populations here in the sense that anybody in the population is equally likely to run into anybody else in the population. That's obviously not true, but it's a starting point. It gives us the assumptions that we need to make progress. And so the number of contacts per infected person is just the number of people you would run into in a day that you might then have a possibility of infecting if you're infectious. So epidemiologists estimate, I think in the West, that number's like 5. But it depends on the culture. It probably depends on the time of year. In the middle of summer, that number might be bigger than in the winter. But we're going to assume it's constant and just take it as a value that gets fed into our model somehow. And again, just to emphasize, all of these things that we do are simplifications so we can make progress. Perhaps the simplest place to start is actually at the end and think about recovering from the disease. So how do we recover from the disease? If you look at, or the people in this R category are also removed, so they may be dead. But it's the people who end up in this last group who are recovered or removed. And we can see from our simple diagram up here that the only way to end up in that last group is actually to have been infectious and to have got better. And so what we want to do is work out what this rate of change of recovered people is with time. And to do that, let's think about the example. Let's go back and think about COVID-19. For COVID-19, we estimate that this recovery time, this gamma that I defined, was about 14 days, right? So let's make a simple assumption here. If you've got a group of sick people and they're all going to be better in 14 days, that's the average, right? I'm not being fancy here. I'm just saying the average is 14 days. Some people are going to take 30, some people are going to take 5, but the average is 14 days. Then we're going to assume that every day 1/14 of the people recover. So over 14 days, every person has recovered. Now this is obviously not true, right? If you've got a bunch of people and they're all sick on day 1 and they've all been sick the same length of time at the beginning, then you'd expect hardly anyone to get well at the beginning, recover on day 1 or day 2 or day 3. By day 10, you'd expect lots of people to be recovering. By day 14, you wouldn't expect all of the people to recover because some of them are going to take 20 days. But on average, 1/14 of them are going to recover every day. So this is literally, we're taking an average, right? And this is a ridiculous assumption, but it lets us make progress. So whatever the duration of infection is, we're going to assume that 1/14 of that, 1 over gamma, in fact, of that group recover each day. And so put another way, every day, and the fact that I defined this here in days, I said that people are sick on average for 14 days, that introduced a time variable. That told us that the T here I'm using, the most reasonable way to be measuring time, the unit here, is days. So each day, in other words, for every unit of time in our problem, we expect 1 over gamma, for COVID-19, we expect 1/14 of all of the infected people on that day to recover. Right? And if you think about the long span of the disease, that's not unreasonable because people are getting sick at different times. So the people in the infected group have been there for different times. So once the disease is up and running, if you like, you expect that 1 over 14 days of them will recover in every period of time. And that lets us answer the question, because here's our fundamental mathematical question: what's the rate of change of recovery with time? And the answer is 1 over gamma of the people who are infected recover. Right? 1 over gamma of the people who are infected recover in each time period. In this case, the way I've set it up, it would be days. So we've got our differential equation for the recovered people. There's only one way to become recovered. You move from the infected group. 1 over gamma of the people in the infected group recover every day. Gamma is the duration of infection. So for COVID-19, you'd have 1/14 of I recovering each day. And just to emphasize, because we're moving from the infected to the recovered group can only increase in size. And so this is a positive. The rate of change of the number of recovered people with time has to be positive. There's our first differential equation. Let's look at the susceptible group then and ask how they get sick. So to determine how many people get infected, in other words, how people are moving from the group that is susceptible into the group of people who are infected, we have to think about one fundamental question. How many new infections do we expect per unit time? Because answering that question will let us fill in this derivative. And that's really mathematically our goal here. What's the rate of change of susceptible people with time? Now, there's only one way to move out of this susceptible group, and that's to move into the infected group, right? Following the arrows, we can only go from susceptible to infected. So to do that, we're talking about the number of new infections. So let's concentrate on new infections, and that'll allow us to decide how many people are leaving the susceptible group and entering the infected group. We've already introduced the basic model parameters you see down at the bottom here, so we can use that information to build the following thought experiment for each infected person. Because we know each infected person is going to have K contacts per unit time. I didn't explicitly express this down here, I didn't have enough space, but this number of contacts is per unit time. So this is a kappa, right? Greek letter kappa. So we've got K contacts per unit time for every infected person. And each contact has a probability of leading to a new infection given by this Greek letter tau. So for each infected person, the number of new infections per unit time is the product of these things, because each infected person is going to run into kappa people. Okay, so kappa people, that's the number of contacts, but just running into a person in the population isn't enough. I'm going to run into 4 people, but not all of those people can be given the disease. So the ones that I'm interested in are the ones who are susceptible to the disease. So the fraction of the population that's susceptible to the disease is what I really need, right? Because then, say for example, kappa is 4, so every infected person runs into 4 people. Well, if only half the population is susceptible, this factor of a half is going to multiply by the 4 to tell me I've only got a chance of getting 2 infections. But not every one of those contacts is going to give an infection. There's a probability for that, and so I have to multiply by the probability of infection. So overall here, we have the total number of contacts between each infected person and a susceptible person, multiplied by the total, or to the probability that that contact is going to lead to a disease. So that's the number of new infections per infected person. So to get the total number of new infections, I take this number of infections per infected person and I multiply it by the number of infected people. And that product together is going to give me the number of new infections. And the number of new infections is precisely equal to the number of people who are leaving the susceptible group and entering the infected group per unit time. Since this is the change in the number of new infections with time, right, it's the number of new infections per unit time, that means it's equal to the rate at which new infections are increasing, with the rate at which I is increasing because of new infections, which means it's the rate at which people are leaving the susceptible group. So the rate of change of the susceptible group is the negative of that number, and the rate at which the infected group's growing because of new infections is equal to this number. And we'll put these together for new infections in a minute. But the important thing is we've seen that the rate of change of new infections is going to be precisely this quantity. And it's going to be negative. This is always negative because the number of susceptible people must always be decreasing, right? You're either staying susceptible or you're becoming infected. There's no way to get back into that group, which means the group of susceptible people decreases or, best case scenario, doesn't change at all. So let's have a look at how we model the number of infected people, given that we understand what's happening to susceptible and removed recovered people. Okay, to complete our model, what we need to do is take what we've got for the recovered and susceptible group and work out how the infectious group is changing. We see from the model here that there's only one way to move from susceptible into infected. There's only one way to get infected people, and that's through this route. So this is the rate of change of susceptible people. And so as we just discussed, the rate of change of the number of infected people must have the same magnitude because it's the same people, but it'll be positive because it's increasing the number of infected people. And so the rate of change of the number of infected people is going to increase because of these new infections. And these people are coming directly from the susceptible group. And then once they've been in the infected group for a while, presumably a time gamma, because that's the average time of infection, then those people will move into the recovered group. So they will leave the infected group, and that will create a new term on the rate of change, and that term will represent the number of recovered people. And again, for both of these, this is per unit time because that's the way we set this thing up, per unit time. And so this is our rate of change of infected people with time. New infections occur because of the susceptible people getting sick. People recover, and so that removes people from the infected group. To simplify this setup, what I'm going to do is introduce a couple of new variables. I'm going to define A to be the combination of variables that live in this term that aren't our fundamental quantities S and I. So there's a kappa tau over n. That's going to be A. So this first term is just going to simplify to A times Si. Right? And the term up here is just minus A times Si. And then for simplicity, I'm going to call 1 over gamma B. So this is just 1 over the length of infection. So this term is just going to be B times I, and this term over here is going to be minus B times I. And so we've now simplified those equations a little bit, and we can rewrite our final SIR equations. And so here's our final SIR model. The rate of change of S is just minus ASI. The rate of change of I has that same term, minus BI, so increasing infections, recovered people, and then the rate of recovery is there. Notice that when you combine those three equations, if I ask what's the rate of change with time of S plus I plus R, well, this term and that term will cancel, this one and that one will cancel, the rate of change is 0. Another way of saying that is that this thing is equal to a constant, and that constant is the total population, because the total population in this model doesn't change. That was one of our assumptions. So our final set of differential equations naturally embodies this idea that the total population is constant. The number of people in those groupings will change over time, as governed by these differential equations, but the total population stays fixed. Every person who begins in one of these groups ends in one of the groups. So that's our model. Notice that the A and the B can be completely determined from parameters of the disease that we're interested in. Gamma is the length of time of the disease. So 1 over gamma for the COVID-19 might be something like 1 over 14, and the units is per day. This term is the number of contacts times the probability of infection divided by the total population. And so these again are all either about the population we're drawing from or the properties of the disease itself. So we'll look later at some properties of these differential equations, what they tell us about the spread of diseases that obey this system of equations, and we'll look at some applications. Well, I hope this has been interesting. Again, if you have any questions, let me know. Thanks for tuning in. I'll see you soon.